Talk about Boyle's law and ventilation. Boyle's law is one of the three gas laws that we're going to use to explain pulmonary function. And Boyle's law specifically refers to, or is the law that we use to help explain how ventilation works. And again, ventilation in the broadest sense is simply breathing, right? We can talk about ventilation of particular lung regions. That's a local control. We can talk about that later. But right now we want to talk about essentially how we move air in and out of the lungs, right? And so we're going to use Boyle's law to help explain that. And Boyle's law basically states that pressure is a very simple law. Pressure is inversely proportional to the volume of the container, right? And so in this scenario, the volume of the container is the lungs. And yeah, I've drawn two sort of schematic lungs down here, and I know that we have two lungs, not one lung, but we're just being very general here to sort of understand the principle. And so really the idea here is that we have a container, right, the lungs, that has a variable volume, right? We have the ability to change their volume. And when we change their volume, as you can see in the equation here, the volume and the pressure are inversely proportional, right? Remember, this fractional relationship means what's on the bottom over here is inversely, right? So volume is inversely proportional to pressure. So what that means is as we go from the left image here to the right image, right, the volume goes up, so the pressure in the lungs would go down, right? Okay, so now how are we going to use that principle to help us explain ventilation? Well, it's pretty simple. We have to explain or describe a few pressures here. One of them is the atmospheric pressure. I'm going to call that PATM. So that's the pressure of the air out in the world, right? And it equals about, again, at sea level, about 760 millimeters of mercury. And millimeters of mercury is a common unit. There are a few other units that are used sometimes, but we're going to stick with millimeters of mercury, right? And again, that's a constant. Unless the weather changes, it can shift a little bit, or you go to higher altitude, then it would fall. But as you sit in one location, and the weather's not dramatically changing, atmospheric pressure is relatively constant. Okay, the other pressure that we need to describe is PALV, or alveolar. We call that alveolar pressure, or some people say intrapulmonary pressure, right? Intra meaning within the lungs. Okay, and so really the relationship between these two pressures is going to determine whether or not air will move, because what moves fluids, what moves gases is a pressure gradient, right? So we need a delta P, right? That's a pressure gradient, delta meaning the change in or the difference in. We need a difference between P1 and P2, right? Because if atmospheric pressure and alveolar pressure are the same, right, then 760 minus 760 equals 0. There is no delta P, and there would be no air movement. That actually does occur during ventilation at specific points, right? But at that point, no air would be moving. So how do we get these pressures to change? Well, as I said, we don't really get this pressure to change. That's the world around us. It doesn't change dramatically, again, unless we move or the weather changes. We've got a tornado coming, something like that. And again, even then, we would just adjust our lung function to compensate for any changes in atmospheric pressure. So, what do we need to have happen here? Well, let me pick a color. We have our lungs are surrounded by, right? They're encapsulated. Right? Encapsulated is probably not the right word, but they're encased within the thoracic cavity, right? And at the bottom, right, we could give this a little bit of mass, color that in a little bit, right? At the bottom of our lungs sits the diaphragm. Actually, I'm going to put that off to the side. Right, so this is the diaphragm, schematically. And the sides would be made up of sort of trying to give this a little bit of mass over here and over here. Right, so this is our rib cage, right? So that's the thoracic wall. So here's the tricky bit. Our lungs, while they do contain some smooth muscle, they contain no muscle that actually moves air in and out of them, right? So how do you move air in and out of lungs that don't have the ability to sort of contract or expand on their own? As we said, this volume change, right, between the left and the right here is going to be the essential element. How on earth, if the lungs don't have any muscles in them to do that, how does it happen? Well, we have the pleural membranes. Remember the pleural membranes on the outside of the lungs and then on the inside of this thoracic cave. I'm not going to try and draw them, but we'll try to fill this in a little bit, right, with a little bit of blue here, because there's a fluid layer, right? There's a fluid layer in between the lung wall and the thoracic wall, right? That's that intrapleural space between the visceral and the parietal pleura. Go back to the anatomy video, right? There's two membranes, one on the surface of the lungs, that's the visceral layer. There's one on the inside of the container on the thoracic wall and the top of the diaphragm there. And then there's fluid in between them, right? So this is our pleural fluid. Again, our pleural fluid being between the two layers of the pleural membranes, or of the pleural membrane, I should say. Okay, and so the idea here is that this fluid, and I've exaggerated the volume there so that we can point it out, but the idea is that the lungs are sort of stuck to the inside of the rib cage and the diaphragm by this fluid. So the pleural fluid is really important, right, because it generates surface tension. Right? So what that means, the analogy here is if you take a pane of glass, right, we're going to call the pane of glass the surface of the lung, and you lay it on a countertop, right? You could slide it around. It would sound a little rough, probably, right? You'd hear the glass sliding. And if you wanted to, you could grab the edges of the glass. You could pick it up. It would come right off. All right, now take a little bit of olive oil, squirt it on a countertop, and lay that pane of glass down. The countertop here is the thoracic wall or the diaphragm. Squirt some olive oil on the tabletop, lay that pane of glass back down, the lung. Lay that pane of glass back down, right? Slide it around. Does it slide easier? Absolutely, right? So the pleural fluid reduces friction, number one. And if you grab the edges of the glass and try to pull it off the tabletop now, is it going to come off the table? No, it's going to stick like crazy, right? That's this function of the pleural fluid to generate surface tension. We do not want the lung to come off the wall of the thoracic cavity or separate from the diaphragm. And so, okay, so that's part one, right? We have to have the lungs stick to the thoracic cavity. Now, that doesn't mean that that's changing lung volume. They're just stuck together. What does change the lung volume is the fact that the thoracic volume changes, right? And so what I'm going to do is we have muscles that pull our ribs up and outward. Right? Add some arrows here all the way around. Right? And the diaphragm, when it contracts, diaphragm's kind of dome-shaped. I made it a little bit dome-shaped, but when it's dome-shaped, when it contracts, it pulls downward. Well, guess what? We are no longer, right, if these actions are occurring, we are no longer looking at this picture. We're looking at this picture, right, over here. And so volume has increased, which means P alveolar has decreased, right? We just set it up here with Boyle's law. If volume goes up, pressure goes down. Remember, atmospheric pressure is sitting up here at 760 still, right? So our alveolar pressure falls to 759, 758, something less than 760, right? And so all of a sudden we have a delta P. And the pressure on the outside is greater than the pressure on the inside of the lungs. And so we, right? We inhale when that happens. Okay? So we're using change in thoracic volume driven by muscles to drive a change in pulmonary volume, lung volume, to change the pressure gradient between outside and inside and drive ventilation, right? And of course, again, if we want the lung volume to change with the thoracic volume, we have to stick the two together. Again, that's where our pleural fluid and that surface tension come into play, right? Now, you go to exhale. What has to happen? Well, we have to go backwards, right? We have to go back over to the left here. And to do that, those thoracic wall muscles have to relax and the diaphragm has to relax, right? And so, of course, at that point, these would start coming, and these sides would start coming in, the diaphragm would start coming back up, and we would start moving back over to this direction, right? Smaller thoracic volume, smaller lung volume, right? So in that scenario, the volume here is going down. So volume going down, which means alveolar pressure would be going up, right? And so again, right, I'm showing the transition here with the arrows to get to the right, and then I'm showing the transition with these arrows to get back to the left, okay? So again, the thoracic volume changes drive lung volume changes, which creates a pressure gradient between the atmospheric air outside and the intrapulmonary pressure, right, inside to drive ventilation, inhalation, and exhalation. Okay. One other thing I want to throw out here is this, well, maybe two other things. One is this intrapulmonary fluid. Yes, it creates surface tension, which sticks the lung to the thoracic wall, but the lung also has elastic tissue in it that tends to make it pull away from this wall continuously. It's tending to sort of retract away from this wall continuously. So the pressure in this intrapleural space, put a little dot here, right? The pressure right there is negative, right? In other words, think about that pane of glass stuck to the table. Even if you're sort of like paused at the end of a normal inhalation or exhalation, right? Remember, if air stops moving, what's the gradient, right? You pause at the end of a normal inhalation and air stops moving. What's delta P if air has stopped moving? 0, right? You pause at a normal exhalation and what has happened? Again, delta P has gone to 0, right? If there's no delta P, there's no air movement. Now, that delta P is between outside air and the lung air, right? But in this fluid-filled space, in the intrapleural space, the pressure there is less than 0. That is like grabbing that pane of glass and pulling upward without pulling it off the table, right? It creates a negative pressure underneath the glass. That's like creating a vacuum. it tends to keep the lung stuck to the thoracic wall, right? It's creating a negative pressure, sort of pulling the lung back toward that wall. And again, that helps maintain that connection. There are situations where a collapsed lung occurs, right? If you poke a hole, and if we have an injury here where you break a rib, or something pokes a big hole through your rib cage, right? Well, now you can introduce air into this space. Well, air would not, right? It's this filled with the pleural fluid, right? If you get air into that space, that air does not generate surface tension, and all of a sudden this lung would sort of shrivel in this space. In other words, your thoracic cage, right, would look like this. Here's your thoracic cage, and here's your lung, right? Kind of shriveled in there, and the thoracic wall, right? The thoracic wall is going out and back, and what's happening in the lung? Nothing, right? So a collapsed lung does not ventilate, and they have to sort of like, go in, poke a hole in here, or go in through the hole that was already there, I guess, and pull that air out so that this lung will reinflate up against the wall and regenerate that surface tension, right, that we require to have the lung volume change with the thoracic volume, right? So that's called atelectasis. A simple term for it is a collapsed lung, okay? Oftentimes, they can occur for a multitude of reasons. If it's due to air, it's called a pneumothorax. You may have heard of that term. Pneumo, referring to air, thorax, meaning your thorax, and it means you get air in your thorax, right? Through this hole that I was sort of indicating would occur if we poke a hole through the rib cage. Okay. Now the final concept here is the term I want to lay out, and it's called compliance. And compliance, or C, and again, I never will ask you to use these equations, but I use the equations because they're shorthand for the concept. If you don't like the shorthand, that's fine. But we need to understand that compliance is the ease with which the lungs can inflate, essentially. And it's basically saying that you get a particular change in volume, up at the top here, delta V, with a particular change in pressure. So if compliance is high, you would have a large change in volume with a small change in pressure. That's actually what you want, right? You want high compliance. You want it to be easy to move air in and out of the lungs. And I need to go back to that surfactant, right? So remember, the inside of all of these, millions and millions and millions of little tiny alveoli, right? Draw a couple of them over here. Right? Those little tiny alveoli, we had surfactant produced. And surfactant reduced the surface tension inside the lung, inside the alveoli. And what that does is it keeps those, the fluid inside the alveoli. There's a thin layer of fluid in there, and it keeps that fluid from pulling inward and collapsing the alveoli. If that were to happen, our compliance would go down, right? The change, we would have to have a bigger change in pressure for a given change in volume, because the alveoli collapse and they have to sort of be reinflated, or at least the small bronchioles collapse and need to be reinflated with each breath. That actually happens in premature babies. Lungs are one of the last organ systems to sort of fully develop. And one of the things that does not develop until late in pregnancy is the production of surfactant. So preemie babies are born, and their compliance is low because they don't have surfactant, right? And so they need to either be given artificial surfactant, or they put them on positive pressure breathing, which means they boost the pressure that they're breathing of the air they're breathing inward. That sort of helps keep the lungs inflated. And you end up, if they don't treat it, you end up with what's called infant respiratory distress syndrome, right? Sometimes, it just makes it difficult for the infant to breathe. Number one, the infant is tiny, and weak, and it's sort of breathing is more strenuous when compliance is low. So we want compliance to be high. And so the key point here, right, is that on the inside of the lung, surfactant keeps surface tension low, right, to keep compliance high. Whereas on the outside of the lung, the pleural fluid, we want surface tension so that our lung sticks to our thoracic wall. Right? So two scenarios for surface tension, one where we want it low inside the lung, and one where we really want it to be high outside the lung. All right, make sure you keep those straight. There's Boyle's law and ventilation.